Friends, welcome to the 9th lecture titled Environmental Loads. In the first part of this lecture, we will discuss some complexities that arise because of conventional environmental loads that acts on offshore structures. Once we understand this, we will slowly move on to the special loads, their complexities and the response behavior of platforms under special loads, then we will lead towards fire resistant design, etc. So, today we are going to talk about environmental loads as the first part of the lecture. Environmental loads have actually two components. One is they vary with space, they vary with time also. They are generally classified based on two factors. One, physical phenomena causing them, the second factor is uncertainty of the loads, which is generally accounted in the design using safety factor. When we look at the variation of environmental loads with respect to time, again there are two kinds of variations. One can be your macro scale variation, which generally do not affect the structural response. The second one is the micro scale variations, which affect the structural response directly. Under macro scale variations, we can give certain examples. Let us say average wind velocity over a specific period of time usually this duration of loading is about 10 minutes. The second variation in macro scale could be tidal current, it could be significant wave height, and peak period of the wave spectrum. The fourth could be peak ground acceleration of the earthquake motion. So, they all come under what we call macro scale variation. They do not actually have direct influence on the response of the structural system. On the contrary, If you look at microscale variations, these variations are so rapid that it makes significant influence on the response of the structure. Let us say in our case the platform. Generally, microscale variations give rise to dynamic effects on the platform. Let us enter conventional and environmental loads. Let us talk about wave loads. The wind generated sea surface waves can be represented by a combination of regular waves. So, what it may be a combination? Regular waves of different amplitude, different period and different wave directions are combined to represent the wave load acting on offshore platforms. The question comes, how actually they are represented? Wave forces are generated based on the water particle kinematics like horizontal water particle velocity, horizontal water particle acceleration, vertical water particle velocity, vertical water particle acceleration. The foremost theory which we all know is Airy's theory. This is also called as linear wave theory. Because it assumes linearity between the kinematic quantities and wave height. It usually assumes a sinusoidal form with wave height h which is very small compared to wavelength lambda. And very small compared to water depth. So, these are some basic assumptions which classifies Airy's theory as linear wave theory. So, according to this theory, if the sea surface profile is explained as a sinusoidal wave, with the water depth represented as small d. The sea surface elevation eta, where x and t varies in space and time, is given by where h is the wave amplitude, k is called wave number, which is generally given by 2 pi by lambda, where lambda is called wavelength, which is approximately 1.56 t square, where t is called wave period, omega is wave frequency, which is 2 pi by t, and Cp is called phase speed, which is omega by k, which is lambda by t. Once I know the sea surface profile, when the water particle is moving horizontally in x with respect to the space and respect to time t, it generates as the water particle moves, because of the wind action on sea surface elevation, they generate horizontal water particle velocity and vertical water particle velocity. Let us say in meter per second. Horizontal water particle velocity is given by omega h by 2 cos hyperbolic k y by sin hyperbolic k d cos k x minus omega t. Vertical water particle velocity is given by omega h by 2 sin hyperbolic k y by sin hyperbolic k d sin k x minus omega t. Differentiating this with respect to time, we get horizontal water particle acceleration, which is omega square h by 2, of course cos hyperbolic k y and sin hyperbolic k d will remain unchanged. There is a minus sign and that becomes cos k x minus omega t. There is another minus sign with this omega, that becomes plus an omega square. Whereas v double dot x of t is minus omega h by 2 sin hyperbolic k y by sin hyperbolic k d of cos k x minus omega t. So, there are some limitations where this theory can be applied. Airy's theory is valid only up to mean sea level, but interestingly there is a complexity here. When you have a cylinder or a leg of a platform whose diameter is very large, there may be a possibility part of the wave may be in submerged position with respect to the cylinder. So, there is a possibility that the cylinder may occupy a position which may be in the trough part. So, the differential submergence effect of the cylinder with respect to the mean sea level is not accounted. So, we call variable submergence effect, because Airy's theory computes the water particle kinematics only up to mean sea level. The variation because of the sea surface elevation with respect to the mean sea level is not accounted in Airy's theory. In that case, the solution is, people have used something called stretching modifications. This will account for water particle kinematics up to the actual level of submergence. Before that, let us see some classical definition which are again complexities in defining these wave theories. There are some classifications said in the literature as deep water, shallow water and intermediate water depth. In this case, the classical definition says, if the water depth is greater than lambda by 2, where lambda is the phase length, then we call this as deep water. The characteristic of deep water is phase speed which is Cp, that is omega by k, is independent of depth. Under this condition, shallow water classically says, if the water depth is less than lambda by 20, then it is classified as shallow water. The characteristic of this is that phase speed depends only on water depth. But it is not a function of lambda. In case of intermediate water depth, the definition says it is between these two values. In this case, phase speed will be influenced by both water depth and period or wavelength. Having said this, let us now talk about the stretching modifications. Friends, we are looking into the completeness of estimating wave loads to some extent, so that we really understand the complexities present in the conventional environmental loads acting on offshore platforms before we discuss in detail about the special loads acting on them and the response behavior of offshore platforms under these special loads. So, under the stretching modification, the first classification what we will see is Wheeler's modification. This is given by Wheeler in 1970. Irregular waves. Journal of Petroleum Technology, page numbers 359, 367. It actually modifies or modified the horizontal water particle velocity and accelerations to account for the variable submergence effect. So, the modified horizontal water particle velocity is given by So, you can very well see this is actually the modification which has happened, and the acceleration part omega square h by 2 cos hyperbolic k y d by d plus eta sin hyperbolic k d sin k x minus omega t, where if this is my sea surface elevation, y is measured from here, if this is my sea bed, this is my water depth t, and this is my eta, which is sea surface profile, which is used here. The second modification was given by Chakrabarty, called as Chakrabarty's modification. This was given by S. K. Chakrabarty in 1971. Discussion of dynamics of single point moorings in deep water. Journal of Waterways, Harbour and Coastal Engineering Division, ASCE 97 WN3 558 590. According to this modification suggested by Chakrabarty in 1971, the horizontal water particle velocity is modified as So, the modification is in the denominator as you see from this equation, differentiating to get the acceleration. We get two equations now suggested by Chakrabarty's modification. Now, interestingly, let us extend this discussion to understand the further complexities in wave loads. In general, when we calculate wave forces, wave loads are assumed to be based on a classic theory saying the C state is a short time period. Short time in sense which is typically of 3 hours. Duration is an idealization. It is also assumed to be a zero mean process. It is also assumed to be following a Gaussian distribution. And it is said to be an ergodic process. Short time period is defined for a specific duration. To some degree, as engineers we accept this. Zero mean process is essentially the statistical distribution of the mean of the wave height, where the amplitude is equal with respect to a mean line. So, let us say this is my mean line. Gaussian distribution is useful because the statistical properties associated with this are important in estimating the characteristics of the wave loads. Let us slightly talk more about these two to understand the complexities. Now, to understand what is ergodic process and stationarity in a given wave load, let us take an example. Let us say I have a wave stream which is varying in amplitude, time and direction. So, let us say this is my t and this data in the vertical axis eta 1 of t. Let us take another history which is again t 2. In the vertical axis of this plots eta 2 of t. Let us take one more time history which is t 3. On the vertical scale of this, it plots eta 3. We are in the process of explaining ergodic process. Let us take up a specific scale here and draw a line and draw another line. At intervals of tau, along this we try to work out the values. We try to work out the values, this value and this value. Once I have these values statistically with us for a good sample, this is my sample which I can call as ensemble in statistics. So, what we did is we drew lines across the random records at intervals tau. Then let us try to find the mean square value of these records. If this mean square value is unique across the ensemble, then the process is called stationary. So, what is ergodic? Ergodic is a special stationary process which has the same mean square value as that of the unique mean square value. So, ergodic is a single sample. So, out of the sample eta 1 of t, eta 2 of t, eta 3 of t, etc., you can pick up any sample. This particular sample chosen for your analysis is called as ergodic when the mean square value of the sample is exactly same as that of the unique mean square value which we found out at intervals of tau along the entire ensemble. So, this is one of the basic assumptions we have in terms of estimating wave loads on offshore platforms. The issue now comes here is wave loads have wave amplitude as a variation, wave period as a variation, and of course, wave direction as a variation. One is interested to find out the maximum force on a given member. So, the interest is determine the maximum force maybe on a member, let us say on an offshore member, structural member. Okay. How to do this? Consider a surface piercing cylinder. Example could be pile of a structure, leg of a jacket platform, we know that on this member combined drag and inertia forces are acting. Both of them varies with time. And it is interesting that at a specific occasion this may be maximum. So, one is interested to know that maximum load. Therefore, in order to find the maximum force, phase angle at which this will occur should be first determined. So, we all know that the total force on the pile member is arising from the velocity and acceleration components of water particle. Let us obtain this force vector and integrate it between the boundaries. So, let us say what are the boundaries within which we should integrate this, especially the boundaries are from the sea surface to seabed, that is 0 to minus h. So, the total force is given by half rho C d dia pi square h square by t square cos theta sin hyperbolic square k h sin hyperbolic 2 k h by 4 k plus h by 2 minus C m rho pi d square by 4 2 pi square by t square h sin theta by k. This equation is obtained by substituting the horizontal water particle velocity and acceleration as obtained by Airy's theory until mean sea level without considering the stretching modifications. To find the maximum force, I should find the differential of this unequated to 0, because we know the variation of the force total is with respect to the angle theta. So, once we do this and substitute, I get theta max as sin inverse of minus pi d by h C m by C d twice of sin square k h by sin hyperbolic 2 k h plus 2 k h. Once I know the maximum phase angle, then I can find by substituting theta max in equation 1, one can find F total, which is going to be the maximum. So, this will have a specific occasion where both inertia and drag forces are maximum for a given offshore cylinder. The second complexity which arise from computing wave forces on members is effect of phase lag on the wave forces. Interestingly, offshore structures have large water plane area, which means that spacing between the members encountering forces the lateral forces. In this case, it is actually the wave force, could also be very high. Let us take for example, a tension leg platform. We say the size of the platform is about 90 meter by 90 meter, resting on 4 columns. So, if this is the plan of a TLP, if this is my x axis, this is plan. So, the center to center distance between the legs or the column members is about 90 meter in the wave direction. So, therefore, the phase angle theta could be 2 pi by lambda delta x, where delta x is the distance between the locations where the wave encounters a structure, and lambda of course is the wavelength. So, if delta x is 90 meter, as in the case of a TLP example, and for a wave period of 10 seconds whose lambda is approximately 1.56 t square, which is 156 meters, then theta actually is 2 pi by 156 into 90, which is about 1.2 pi, which can have a global amplification. It may result in cancellation of forces, because it is 1.2 pi. What does it mean? It is important now to note, it is important to note that the geometric spacing of the members is also governed by the wave forces acting on them. Please understand, that is why I said offshore platforms are form dominated design. It is not that you assume a structural form and then find the stresses or forces on the member. It is you design the structural form, in sense the spacing of the member such that the wave forces on the members gets cancelled. So, it is form dominated design. So, that is very interesting that one can use intelligently the choice of spacing of the members, so that the forces acting on these members can compromise on each other. So, friends, in this lecture we are discussing about the complexities on conventional environmental loads. We picked up for discussion the wave loads, and we saw how wave loads and stretching modifications can be found, can be seen from the ready equations, and we also slightly understood the complexities arise because of the phase angle and other factors that influence the forces on the offshore members. Thank you very much.